Okay, I hear the recording in progress. Okay, so I should be finishing 11.2 today, start some of 11.3. So schedule-wise, I think I'm a little bit ahead. So we're up to here. Let me go ahead and mark this off. 11.2. I'll do a couple problems at the end, which are geometric series involving variables. And then I'll start 11.3. And you'll get a quiz tomorrow. It'll be on 11.1 and 11.2 material. Okay. Usual rules for quizzes. So you have until 11:59 p.m. to submit it, open everything, but work it out like we did in class, okay? All right, so game plan for today is knock off a couple problems from here and start 11.3, which is on the integral test. You'll see that shortly. Okay, so back to 11.2, some problems at the end. Page 716. 57 through 63, find the values of x for which the series converges, find the sum of the series for those values of x. So there's x involved, there's a variable involved here. And you say, well, how do you know if the series converges or diverges? Well, it depends on what x you have. Okay? That will be a main theme for most of the rest of this chapter. You'll have some series, but there's an x in there. You say, well, is it going to converge or is it going to diverge? It depends on what you have for x. And we'll see criterion for, okay, when do I know I have a convergent series? We get a number, or when do I have a divergent series? Okay, so I'll show you a couple of problems from 57 to 63. Okay, so here is 59. Summation n equals 0 to infinity. Yes, you can start at 0. And later on, toward the end of this chapter, we're almost exclusively going to start with n equals 0. Okay, I can rewrite it like this. All right, so I write some of the terms out. And yet we highly suspect that this thing is going to be the common ratio because it's going to be this thing to the 0 power, to the 1 power, 2, 3, 4. So in essence, you keep multiplying by x minus 2 over 3. Okay, so I plug in 0. Anything to 0 is 1. Plug in 1, 2, 3, and so on. So clearly the common ratio is x minus 2 over 3. Well, is this series going to converge or diverge? Well, this being a geometric series, this will converge if this thing is between -1 and 1. So I solve x minus 2 over 3 between -1 and 1. Multiply both sides, multiply all three sides, I should say, by 3, and add 2. So that means this series will converge if x is between -1 and 5. Okay. And notice it's not including -1, not including 5. Okay, just a quick note, if I did plug in 5, 5 minus 2 is 3. I have 3 to the n over 3 to the n, which is 1, which means I'm just summing up 1. So the series is 1 plus 1 plus 1 plus 1 plus 1, infinitely many times, that diverges. If I plug in -1, I would have -3 to the n over 3 to the n. That's -1 to the n. The series becomes 1 minus 1 plus 1 minus 1 plus 1 minus 1. So that diverges, that does not approach any one number. The partial sums bounce back and forth between 0 and 1. So we do not approach any one number. Okay, then what is the infinite sum? If x is between -1 and 5, I just use the formula. So the sum is a over 1 minus r. A is the first term, 1 over 1 minus the common ratio is x minus 2 over 3. A little bit of touch up, multiply top and bottom by 3. 3 over 3 times 1 is 3, minus parentheses x minus 2. After you distribute, 3 over 5 minus x. Okay. I'm going to show you one more like that, 61. All right, so summation n equals 0 to infinity, 2 to the n over x to the n. Plug in 0, you get 1. Plug in 1, 2 over x. Plug in 2, 2 squared over x squared. Plug in 3, 2 cubed over x cubed, and so on. The common ratio is 2 over x. Okay. This is a little bit trickier, but we want -1 to be less than 2 over x, which is less than 1. It's probably easier to think of the graph for this one. So here's the graph of y equals 2 over x. Okay, here's the point 2, comma 1. And here's the point -2, -1. Okay, so I want the graph to be less than 1. Well, that would be from 2 to infinity. But greater than -1. Greater than -1. Well, that's from -infinity to -2. Okay. So where will this series converge? From -infinity to -2, union 2 to infinity. Okay, so for instance, if I plug in 3, the common ratio is 2/3. That's less than 1. Or if I plug in -3, I'm also good. But I cannot plug in, let's say, 1. That would make the common ratio 2. And I can't plug in a -1. That would make the common ratio -2. All right, so where does the series converge? From -infinity to -2, union 2 to infinity. Okay, and what is the infinite sum? A over 1 minus r. First term is again 1, very nice, over 1 minus a common ratio, which is 2 over x. Clean it up, multiply top and bottom by x over x minus 2. Okay, so what is the infinite sum? X over x minus 2. All right, and that is that. Okay, so I'm now done with 11.2. So if I were literally to follow the schedule, I'd be done for the day. But as you know, I don't like to do it that way. I'll go ahead and get started with the next section, planning ahead, in case something messes up later, or I get sick, I fall behind, or internet goes down and whatnot. It's nice to get a little bit ahead. So I'll get started with some of 11.3, which is on the integral test. As you might expect, you have to do some integration for this section. Okay, page 719. Integral test. It says in estimates of sums. We're not going to do the estimates of sums. We'll just do the integral test. Let me state the integral test. You can put this on your cheat sheet if you wish. Page 721. Okay, suppose f is a continuous, positive, and decreasing function. All of these have to be true. And for the functions that we have, that's basically correct. Okay, it's continuous, positive, decreasing from 1 to infinity. Technically, it doesn't have to be 1. You can start at 2, 3, 4, or anywhere. But let's just leave it as 1 for now. And that a sub n equal f of n. We're essentially changing the problem into an integral. I look at this series and say, let me integrate the corresponding series. The series is convergent if and only if the improper integral is convergent. Okay? In other words, if the integral converges, the series converges. If the integral diverges, the series also diverges. And they have the extra note there. It is not necessary to start the series at n equals 1. You could start at 4 and integrate from 4 to infinity. Okay? The main thing is that the function ultimately be decreasing, all of these things, positive, continuous, and decreasing eventually, so to speak. So you don't have to start, like over here, you can't start at 1 because you might have a negative, and you can't start at 3, but you can start at 4. Okay, I'll give you my shortened version of the same thing. It's a little bit less writing. So what I have is more compact. It saves you space on your formula sheet anyway. Okay, so here's the essence of the integral test. Change the summation of a sub n. Notice a lazy notation, n equals 1 to infinity or whatever. Change into a corresponding integral. Integral from 1 to infinity of f of x dx. So how do you know what to integrate? You basically just copy this over here. It's just that for series, you usually see an n. But for functions, we change it to x. Just change it to a function of x. Okay. F has to be continuous, positive, decreasing. Here's my abbreviation, cont, positive, decreasing arrow down. Okay. And I think you can catch what I mean by here. Same thing as what the book has, but very more compact. If integral converges, then series converges. Integral diverges, then the series diverges. So you may use this abbreviation on all of the things that you do for me. So quiz, you can do that. Homework, you can do that. Test, you can do that. Final exam, you can do that. It means integral converges, series converges, integral diverges, series diverges. Okay. Heads up that maybe your next math teacher is going to make you write it all out. Okay. Obviously, whoever your next math teacher is, you got to follow their rules. Okay. And you say, oh, my teacher let us use all these abbreviations. That's fine, but your next teacher might insist that you write the whole thing out. Okay. I'm just doing it more compact because you're going to be writing it so many times, you just get tired of writing the whole thing, right? And if we all know what we're talking about, right? Integral converges, series converges. Integral diverges, series diverges. We know we're talking about series and sequences, so this doesn't mean, intensive care or, identification, South Carolina, South Dakota. We know what we're talking about. Integral converges, series converges, integral diverges, series diverges. Essentially, whatever happens to the integral will happen to the series. Okay. I'll give you a little bit of a justification of it as to why it works. Okay, let's see. For the divergent case, whoops. Okay, let's start with this. This is the convergent case, sorry. Bottom of page 719. Okay, when we go A1, A2, A3, A4, and so on, we're basically thinking of this as rectangles, all with a base of 1 and the height of AN. Okay, so this is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, and so on. Okay. Suppose we already know that this integral converges, y equals 1 over x squared. Okay. The infinite area converges. We did that in a previous section. And you look at the picture. Okay. How can the area of these rectangles go to infinity if something bigger than that converges to a real number? Right? Yes, this was left out of the picture, but we know this is finite area. We can always go back and add this area later. Okay, so the idea is that the integral converges, so the series also has to converge because it stays below something which converges. And then in the divergent case, you go the other way. Okay. So this area is 1 over radical 1. So this is like A1, A2, A3, A4. All the rectangles are bigger. That's why we insist on continuous, positive, and decreasing. Okay. And we know that we have an infinite amount of area under the curve. If we have an infinite amount of area under the curve, these rectangles are above. Well, that cannot converge. Right? How can the sum of the areas converge if the sum is above the area under the curve, which I already know is infinite? Okay. Now, if you didn't understand this analysis, that's okay. Some of you maybe got it, some of you didn't. It was my responsibility to show it to you. So there, I showed it to you. Okay. Bottom line, what do you need to know for exams, right? If the integral converges, so does the series. If the integral diverges, so does the series diverge. So whatever happens to the integral, the same thing will happen to the series. Okay. So, quick example. Show that the harmonic series diverges. Okay, so I showed you a little mini proof last time where you kept adding halves. You can be shown that you have a half plus a half plus a half plus a half infinitely many times. It's a little bit cleaner to show you with this integral test. Okay, so the harmonic series, you want to mark this down. The harmonic series is summation n equals 1 infinity of 1 over n. It is sum of the reciprocals of the positive integers. So it's 1 over 1 plus 1/2 plus a third plus a fourth. Okay, so we look at the corresponding integral. So how do you know what to integrate? It's basically 1 over n. You just change it to 1 over x. Okay, so this is what I mean by, for series, we usually use n, although sometimes the text uses k. For functions, just change it to x. In other words, just change 1 over n to 1 over x. 1 to infinity. Okay. We did a section before on improper integrals. This is limit b approaches infinity of the integral from 1 to b of 1 over x dx. Limit b approaches infinity of ln absolute value of x from 1 to b. B is positive, so I can drop the bars. 1 is positive, I can drop the bars. So it's limit b approaches infinity of ln b minus ln 1. Ln 1 is 0. And that limit is infinite. Since the integral diverges, the series also diverges by the integral test. So that's what we're saying. Okay, so believe it or not, you have an infinite amount of area under here, and that also means that this series diverges. Let's look at another one. How about summation of 1 over n squared? Does that converge or diverge? Okay. Just writing some of the terms out, it's 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared. Okay, in case you're wondering, you might say, why don't I just do the rule for geometric series? And there's a very simple rule for that. This is not geometric. You don't keep multiplying by the same thing throughout. This is 1 over 1 plus 1 over 4 plus 1 over 9 plus 1 over 16. You don't keep multiplying by the same thing all the way through. So I cannot use the rule for geometric series. But I'll do the integral test. So what do I integrate? Instead of 1 over n squared, 1 over x squared from 1 to infinity. Okay, that's a limit as b approaches infinity of the integral from 1 to b of x at a negative 2 dx. Integral of x to negative 2 is x at negative 1 over negative 1. Limit b approaches infinity, x at negative 1 over negative 1 from 1 to b. Take out the negative, that's negative limit b approaches infinity of 1 over x from 1 to b. Okay, negative limit b approaches infinity. Plug in b, 1 over b minus 1 over 1. And now when b gets big, this approaches 0. So I have negative of negative 1, which is 1. So, quick key statement, since IC, SC, since the integral converges, the series also converges by the integral test. So here's the kind of thing you want to write for me on homework, quiz, exam. Okay, this converges because blah, 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 or the series diverges because blah, 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 blah. So since the integral converges, the original series also converges by the integral test. And a quick word of caution, we cannot say that the series converges to 1. Quite often we're left with the conclusion that the series converges, period, and yet we don't know what it converges to. Okay? And a side note, it turns out that this series, summation n equals 1 to infinity of 1 over n squared, turns out to be pi squared over 6. That's beyond the scope of our course to know how we got it, although it is kind of close to 1. It's 3.1 squared, that's about 9 over 6, about 1.5. Okay, so it's in the neighborhood of 1. We don't know how to do it in our course. Okay, so when you do the integral test and you say the series converges, that's all you can say. So the integral in this particular case converged to 1. All we can say is that the series converges, period. We cannot say the series converges to 1. In fact, most of the time it will not converge to the same number. Okay, so if you look at this picture over here, y equals 1 over x squared, and what's kind of weird, you might think, it has the same basic shape as 1 over x, right? 1 over x looks like that. 1 over x squared looks like that. Here you have an infinite amount of area. You get all the area that you want. Here you're bounded by 1. In fact, we would say the total area from 1 to infinity is 1. Okay, now I'll show you one more. So we have 1 over n, the harmonic series, diverges. 1 over n squared converges. Okay, the next one, I'm going to pick something where an exponent is just a little bit more than 1. This is like 1 over n to the 1. How about 1 over n to the 1.01? So by the integral test, compare it to this thing. it's not that far apart from this, you might think, right? 1 over x, that's like 1 over x to the 1. This is 1 over x to the 1.01. And yet, let's see what happens. So we know how to do this improper integral. Limit b approach infinity, integral from 1 to b, x to the negative 1.01 dx. The key thing is after I integrate, when you do the power rule, right, you add 1, you're still going to have a negative exponent. That's the key idea. So limit b approaches infinity, x to the negative 0.01 divided by negative 0.01. Dividing by negative 0.01 is the same as multiplying by negative 100. Limit b approaches infinity, 1 over x to the 0.01 from 1 to b, which is negative 100. Limit b approaches infinity, 1 over b to the 0.01 minus 1 over 1, which is 1. And now here's the thing again. When b gets super big, this approaches 0. So I have negative 100 times negative 1, which is 100. So therefore, since the integral converges, the series also converges by the integral test. Okay, so 1 over n, series 1 over n converges. 1 over n to the 1.01. Sorry, this one diverges. This one converges. I could do the same logic if I had 1.01, okay, ever so slightly bigger than 1 over n. This would still converge. So it's almost like the cutting edge of infinity, the limit of getting an infinite amount of area is 1 over n. As soon as I make it 1 over n to the 1.01, the series will converge. That's really weird, in my opinion. You literally have the cutting edge of infinity. 1 over x, infinite amount of area. If I just go ever so slightly lower for a function like this, suppose I put x to the 1 point, put a million zeros and then a 1. That will all of a sudden converge. Okay, that's really weird. So this is just the limiting function of an infinite amount of area. If I just go ever so slightly below it with 1 over x to the 1 point billion zeros followed by 1, that series will converge. Okay, so that leads us to a rule called P series. And you want to put this on your formula sheet also. Page 722. P series for a particular power. Put this on your cheat sheet. Again, heads up, if we were meeting face to face, I'd make you memorize it. The P series, something that looks like summation n equals 1 to infinity, 1 over n to the p. It's convergent if p is greater than 1, divergent if p is less than or equal to 1. Okay. Remember, if we have p equals 1, that means you have 1 over n. That is our harmonic series. And by comparison, if I have p less than 1, like p is 0.05 or 0.01, that would still diverge. Okay. The cutting edge of convergence or divergence is p equals 1, diverges. If p is 1.001, the series converges. Okay, a couple of quick examples. Summation 1 over n cubed. Okay, that's a p series where p is 3, that's bigger than 1, that converges. How about summation of 1 over cube root of n? That's 1 over n to the 1/3. 1/3 is less than 1. So that's a p series with p equal to 1/3 less than 1. That will be a divergent series. And yeah, this is that side note of what I just mentioned. We should not infer from the integral test that the sum of the series is equal to the value of the integral. Okay, this came out to be 1, but the book has the same thing as I have. This turns out to be pi squared over 6. Okay. So a quick example. It says page 721, number 9. Not sure if that's the same as ours or not, but it doesn't matter. Yeah, it's not the same. Okay, so just treat this as an example. This is from the previous edition. Summation of 1 over n raised to the radical 2. Okay, so this is a p series. The power is radical 2. That's bigger than 1. Square root of 2 is like 1.4. So that converges. So you should have this same kind of language for me on any quiz, test, homework. Okay, convergent, because it's a p series. P is radical 2, which is greater than 1. So again, what does a p series look like? It looks like this. The rule for the p series comes from the integral test. And so we'll do some problems from the integral test, but after a while, for future sections, we're just going to look at this and say, okay, it's a p series. It will either converge or diverge, and not have you go through the formal integration. But since this section we're doing the integral test, we will do the formal integration. All right, so let me go ahead and start showing you stuff. Okay, so 11.3, use the integral test. Bottom of 725. Use the integral test to determine whether the series is convergent or divergent. I'm actually going to change some of the problems. (726), determine whether the series is convergent or divergent. Okay, so trying to see how much do I want to do today. Now I'm going to show you problem 3 star. Summation n equals 1 to infinity of 1 over 5th root of n. Now it says do it by the integral test. Graph looks sort of like that. Continuous, yep. Positive, yep. Decreasing, yep. Looks like that. So I can do the integral test. So how can I tell if this converges or diverges? Look at the corresponding integral. You say, how do you know what to integrate? You basically integrate this, just change n to an x. And you integrate from 1 to infinity. Okay, how do I integrate from 1 to infinity? You integrate from 1 to b, and then take the limit as b equals infinity. Remember we did that in a previous section. And this can be rewritten as x to the negative 1/5 dx. All right, so limit b equals infinity. X to the 4/5 divided by 4/5 means times 5/4. Take out the 5/4. Limit b equals infinity. Plug in b. Minus plug in 1. 1 raised to anything is 1. And then when b gets big, this gets big. Super big minus 1 is still super big. Multiplied by 5/4, it's big. So I get infinity. So conclusion, therefore, dot, dot, dot means therefore, since the integral diverges, the series diverges by the integral test. Okay, so this is the kind of language you would have. This series diverges. And extra thing to note, we already know now this can be written as a p series, a new p series. So let me just mark that. I can write this as summation of 1 over n to the 1/5. And 1/5 is less than 1, which means the series diverges. But here we're practicing the integral test. So I want you to actually do the integration. But this is an example of a p series. Okay. It's summation of 1 over n to the p. Converges, p is greater than 1. Diverges, p is less than or equal to 1. So it's 1 over n to the 1/5 power 1/5 is less than 1, therefore the series diverges. Okay. Okay, and let's see, do I want to do one more? Okay. What time is it? 8:40, got plenty of time. Okay, so I'll set you up with one more, and then we'll probably quit. Okay, summation n equals 1 to infinity, n over n squared plus 1. Do it by the integral test. Okay, so it means you just integrate this thing, change n to x. So instead of n over n squared plus 1, x over x squared plus 1. So n is reserved for series, x for integral. So that's sort of like understood. And technically, there's nothing wrong with saying n over n squared plus 1 dn. It's just not what's normally done. So yes, what you should do for me is to switch the letters to x. That's considered convention. Okay, so if this thing converges, so does the series. If this thing diverges, so does the series. So that's the way the integral test works. Whatever happens to the integral happens to the series. If this converges, this converges. If this diverges, this diverges. Okay. You can graph this if you want to, but you can tell x is smaller than x squared plus 1. It's a rational function, so it's going to be continuous. It's positive. It's decreasing from 1 to infinity. Okay, so I want the limit as b approaching infinity, integral from 1 to b of x over x squared plus 1. Looks like it's a good time for a u substitution. The derivative of x squared plus 1 is 2x. So let u equal x squared plus 1. Du is 2x dx. You need a 2 inside and a half outside. Change the limits. If x is 1, plug in 1, 1 squared plus 1 is 2. Plug in b. Well, all I can say is b squared plus 1 for u. So my new integral is 1/2 in front, limit b approaching infinity. Excuse me. Integral from 2 to b squared plus 1, there's a b there, of du over u. Try to keep this thing focused here. There we go. 2x dx is du over u. So that's my natural log. So 1/2 limit b approaching infinity, ln absolute value of u from 2 to b squared plus 1 equals 1/2 limit b approaching infinity. Plug in b squared plus 1. The absolute value of b squared plus 1 is b squared plus 1 minus absolute value of 2 is 2. And that goes infinity. Okay. B squared plus 1, if b is big, b squared plus 1 is big, ln that is big. Subtract that puny number, it's big. Half of big is still big, so infinity. So our conclusion. Getting a glare here. Maybe that's another reason why I should stop this. Well, sorry if you can't see that. Since the integral diverges, so does the series diverge by the integral test. So since the integral diverges, so does the series diverge by the integral test. And I think I'll stop there. I think I'll get the shade in my room here. But anyway, that should be that. Okay, let me stop the share and I'm done, folks. Let me check the chat if there's any questions. So tomorrow I'll continue with section 3 and you'll also be getting your quiz on sections 1 and 2 for tomorrow's quiz. Okay, any questions, please? Otherwise, we're done. All right, have a good day, everyone, and we'll see you next time. Okay, all right, bye, everybody.